Hello, today's topic is section 4.2, maximum and minimum values. In previous sections, we've thought about reasons why we might want to make a quantity either as large as possible or as small as possible. We talked about profit, the company's profit in producing and selling an item. And of course, the company wants to maximize the profit to figure out how much to produce in order to make their profit as large as possible. A company might also want to minimize cost or minimize average cost. In this section, we explore maximum and minimum values even more. You should read the textbook where a definition for absolute maximum and absolute minimum values is concerned. If I want to talk about just maximum and minimum values as one, I might call them absolute extreme values. So here the word extreme includes both maxes or mins. And then there's also a definition in your book for local or relative extreme values. So again, both local maxes and local mins. Another word that you might hear instead of absolute maxes or absolute mins is global. The idea with an absolute maximum is that it's the largest the function ever is, anywhere in the domain of the function. Likewise, an absolute minimum is the smallest that the function is for all inputs in the domain. On the other hand, local maxes or local mins still correspond to like highest points and lowest points, but only locally. I think you'll see what I mean by this when we look at a graph here. In the xy plane, here's a graph of y equals f of x. And there are some locations on the graph that jump out at me. One of those locations is certainly this point, right, up at the top. Let's call this point B, maybe. The x value is B here. And I see that f of B is the largest value anywhere. And so what I would say is that f of B is an absolute maximum value. Likewise, I see this low point right here on the graph. Let's call this location C. And very clearly, this is the lowest point on the graph. It's the smallest value that the function ever equals. And so what we could say is that f of C is the absolute minimum value. In the book, and as we go through this section and start to maximize or minimize functions, we will want to be able to distinguish between the value of the max or the value of the min itself and also where it occurs. And so if I look at the absolute minimum here, I might say something like f of x has an absolute min at x equals c, and furthermore, the absolute minimum value is f of c, whatever that function value is. Now, there's at least one other point on this curve that is of interest, namely this point right here. It is, at this location, the function does kind of dip down into a little valley. And the height in this location is the smallest of any nearby heights, right? It is the lowest point, not of the entire graph, but of any of the graph values that are nearby. And so if that's point A, what we could say is that the function f of x has a local minimum value at x equals A. And we could also say that the local minimum value is f of a. Sorry. Now, in this graph, we already noted that f has an absolute max at b because it's the highest point on the curve, but it's also the highest point of anything nearby. So not only is f of b the absolute maximum, but f of b is also a local max. And we could say the same thing about this point down at the bottom here. F of c is an absolute minimum, but this is also the lowest point of any of the values nearby. And so not only is f of c the absolute minimum value, like we said before, but f of c is also a local minimum value. We're going to notice that some functions have absolute maxes and absolute mins, so they have both the largest and smallest value. Other functions will just have one absolute min or one absolute max. A function could have neither an absolute max nor an absolute min. And there are all of those possibilities for local maxes and local mins as well. Let's look at some examples. When we think about a function here, like f of x equals x squared, in the back of our heads we really should be thinking about the domain of the function as well. And so if I just write f of x equals x squared, we understand that the domain of this function is all real numbers. Right? If nothing is specified, if there's no restriction on the domain, I assume that the domain is the largest possible domain. So we've been working with x squared all semester long. We know that its graph is the standard parabola, and it looks something like this. What can we say about the maximum and minimum values for f of x equals x squared? Well, for my parabola, it really keeps going up forever and ever and ever in either direction. And so there's no largest possible value. So x squared, as long as the domain is minus infinity to infinity, has no absolute or local maxes, maximum values. What I can see, however, from the graph is that there is a lowest value. Right? This is the lowest that the curve ever is when x is 0. And it's also a local minimum, right? Because it's the smallest value of anything nearby. So f of 0 equals 0 squared is an absolute minimum and a local minimum value of f of x equals x squared on minus infinity to infinity. The fact that we're on the entire real line, in other words, the fact that the domain is all real numbers, is important when we're deciding what the absolute and local max and mins are. For example, what if I look at the same function, f of x equals x squared, but this time I'm going to restrict the domain and I'm going to say that the domain is -1 to 2, including -1 and 2. In this case, what happens? I no longer get the entire parabola as the graph because I'm only looking at the part of it between -1, between x equals -1 and x equals 2. And so in this case, my graph looks something like this. I know that the height at -1 is 1, and if I were to plug in x equals 2, the height at this other endpoint is 4. And so what can we say about the function in this case? Here, x squared has an absolute maximum value of 4. If we're only on the interval from -1 to 2. Right? This is certainly, this dot here is the highest that the graph ever is. At 0, 0, that is still a local and an absolute minimum. So f of 0 equals 0 squared is still an absolute and local minimum value. I can play tricks like this all day long. Let's look at maybe one more, one or two more. Similar examples. So, f of x equals x squared, but this time on the interval from 1 to 2. So there's a different restriction on the domain. I'm just looking at x values between 1 and 2. So in this case, let's say this is x equals 1, this is x equals 2. In this case, I'm only looking at kind of a tiny portion of the parabola. Right? The rest of it would be this dotted line, but I'm not considering that part this time. And so for this curve, what can we say? This curve doesn't have any local extreme values. Your book requires for a local max or a local min that we have to be able to look on either side of the minimum value. And as you can see, for either of these two endpoints, I can't look to the left or to the right. And so those aren't local maxes or local mins. But they still are absolute minimum values and absolute maximum values. So in this case, f of 1 equals 1, right, the height here is 1, is an absolute min. And at the other endpoint, this highest point, f of 2 equals 4, is an absolute max. So this is, I mean, technically it's a different function that we're thinking about each time, although the formula is the same, right? The key is that we're changing the domain and getting different results for what kinds of extreme values we have. Let me look at one more example. Same function, same formula, at least, f of x equals x squared. But this time, let's just look at the open interval from 0 to 1. Right, with the parentheses, I'm not including 0 and I'm not including 1. So what does my graph look like this time? This time, I have an open circle at the origin, and then I'm increasing until x is 1. If that were a filled-in circle, the height would be 1, but it's not filled in. And so this is kind of like what we were talking about when we were talking about limits. In this case, the limit as x goes to 1 from below is equal to 1. But I never reach 1 because it's an open circle. So I don't have an absolute maximum here, right? I do have the value like 0.999999 and 0.9999999, but I never quite get to 1, right? So there's no largest value for the function in this case. And the same can be said about going towards 0. The limit as x goes to 0 from above of x squared is equal to 0, but I never hit 0. So I don't have an absolute minimum or a local minimum. And so in this case, in this example, there are no extreme values. Okay, like I said, there are many different things that can occur depending on what the function is. So, because we want to maximize and minimize functions, somehow we need to come up with a way of deciding when a function is going to have absolute maximum and absolute minimum values. And one result, a very important result, it's in your text, that guarantees that a function has both an absolute max and an absolute min is something called the extreme value theorem. I usually abbreviate the extreme value theorem as the EVT, and it says the following. If a function f of x is continuous on the closed interval a comma b, then the function f has both an absolute max and and absolute minimum, at least on the interval. But, of course, if I change the interval, then the max and min might change. Continuity is something that we've talked about in this class, although I haven't really said the word all that much. A long time ago when we were talking about limits, we called continuity the direct substitution property. And the definition that you read about in your book is the following. F of x is continuous at x equals a if the limit as x approaches a of f of x is equal to f of a. Okay, just to remember that. So, what we'll see at the end of this section is something called the closed interval method. And this is a method that we can use to locate those absolute maxes and absolute minimum values that the EVT guarantees exist. All right, this is something we'll do tomorrow. With the rest of this video, I want to just mention a couple of other things. Let's say we have the function f of x equals x squared, and I'm going to look at one of the previous examples. I'm just going to focus on the interval from -1 to 2. All right, so that's the graph of this function. Looks like this. So, if this is my function, I know that polynomials are continuous everywhere. Another type of function that's continuous everywhere that it's defined is a rational function. In other words, a quotient of two polynomials. So x squared is continuous. The interval -1 to 2 with those square brackets is a closed interval. And so the EVT guarantees that with this example, I have to have an absolute max and I have to have an absolute minimum value. And so if we look at the graph, we can see exactly what the possibilities are for where this happens. So either the function has an absolute max or an absolute min at one of the endpoints, like in this case, or the absolute min, in this case, or the absolute max in other examples, will happen somewhere inside the interval. Right, so here's an absolute max, and it's occurring at an endpoint. And down here at the min, the absolute min is inside the interval. And so I'm going to ignore the endpoint condition for a minute. But instead I want to focus on this minimum that's in the interval. And what's interesting about having a minimum like this inside the interval is that I know exactly what the slope of the tangent line is at this location. Right at the bottom of the graph here, you can see that the graph sort of levels out. And in other words, the slope of the tangent line here is 0. Right? This little red bar is the slope of the tangent line, and it's equal to 0 there. So this suggests something. This suggests that if I want to start to try to figure out where a function has a maximum and or a minimum value, what I might do is take the derivative and figure out where the derivative equals 0. Because that should find locations like this for me. there's a theorem named after a French mathematician that says essentially what I just said. It's called Fermat's theorem. And it's handy in our attempt to locate maxes and mins. It says the following. If a function, let's call it y equals f of x, has a local min or max at x equals c, and if f prime of c exists, then the value of the derivative at this location, where I have either a local max or a local min, has to equal 0. All right, notice that in this theorem, we are requiring that the derivative exists, and the reason for that is because I could run into an example like this. The function f of x equals absolute value of x is not something that we've dealt with too much in this class. But this is a piecewise defined function. It's equal to x if x is greater than or equal to 0, and it's equal to minus x if x is negative. The graph of the absolute value function, you hopefully remember, is a v, essentially, right, at the origin, like that. When x is positive over here, my curve is just y equals x. Over on this side, when x is negative, the curve is y equals minus x, right, the opposite, or the off diagonal. And at the origin, right, I see a local min, which happens to also be an absolute min, but because of this sharp corner in the graph, f prime of 0 does not exist. Right, so when I'm trying to find local maxes and local mins, I should look for where the derivative equals 0, but I also have to pay attention to locations where the derivative doesn't exist, because I might have a corner, like in this example. Another thing that I want to point out about Fermat's theorem is that the converse is not true. In other words, just because the derivative equals 0 doesn't guarantee that I have a local max or a local min at that location. A classic example that shows me why that's not true is f of x equals x cubed. And I'll sketch this for you, and then that'll basically do it with this video. We'll talk about a few other things tomorrow, so make sure you read section 4.2 for tomorrow. If we look at f of x equals x cubed, we should know what the graph is. This is our standard cubic function. Right, the graph looks something like this. Using the power rule, f prime of x equals 3x squared. And if I set that derivative equal to 0, it turns out that x equals 0. Right, so I took the derivative, I figured out where the derivative equals 0. And so I might think that I have a max or a min at 0, but actually I don't. Right, at 0, there are some values smaller than 0 nearby, and there are also values bigger than 0 nearby. So the thing that's going on at 0 for this function is that, yes, the tangent line has a 0 slope, but the curve doesn't, right, it doesn't turn. This isn't a max and it's not a min. Okay, so even though a derivative equals 0, it doesn't guarantee that I have a max or a min, but it helps me in my search.